Hello ladies and gentlemen, this is Mr. Cunningham, and what we'll be talking about today is solutions. But before we get started on that, what I would like you guys to do is make sure you're following along on your notes page, which is 13.1, and what I would like you guys to do is go ahead and try to answer those bell work questions. Those answers will appear for you on Edpuzzle, and then we'll go ahead and get started. Alright, so now that you've taken a chance to answer those bell work questions, again, we're going to be talking about solutions today, and that was kind of like your first question. So it's like, what is a solution in terms of chemistry? So really, a solution is just a mixture. Okay, so you saw this answer on your Edpuzzle and on the bell work questions, but really, it's a mixture of two or more substances. There's something called a solute, and there's something called a solvent. Okay, we're going to be talking about a lot of those things today. So let's look at our goals first and our sub-objectives. So sub-objective 1 says you need to be able to determine and define the components of a solution. Okay, so what are the parts of a solution called? Sub-objective 2 says you need to be able to describe properties of a solution and its properties with another solution. And then your goal is to explain the process of something called solvation and the factors that affect the rate of solvation. So here we go. So these are the desired, I would say, learning objectives for this entire unit. Okay, so overarching things you're going to be looking forward to, looking into the future, is you need to describe the properties and types of solutions, and explain how temperature, pressure, and polarity of the solvent affect solubility. And then you need to be able to calculate different units of concentration, which we will cover in later lessons, and perform calculations regarding dilutions of solutions, and then make a solution using these calculations. So in this section, in this unit, on your test, not only are you going to have to do calculations, you're going to actually have to do some lab portion. You're going to actually make a solution for me. We will have labs set up, and I will say, make me this solution, and you will have to do that. So there will be a lab component to this test. So here we go. Here are some examples of solutions. Air is a solution. Okay, again, we said that solutions are mixtures of a bunch of substances. Okay, so air is an example of a solution. Okay, there's a bunch of different compounds or a bunch of different substances inside of it. Lakes, okay, you've got water and then you've got a bunch of other particles floating around in there. Steel, you might be like, wait a minute, that's not a liquid. Steel's hard, rigid, it isn't a liquid. Well, solutions don't have to be liquids. They just have to contain something called a solute and a solvent. Then you've also got like cell solutions, okay? So like biology, a lot of the chemistry that happens in our bodies takes place in solutions. Ocean water, another example of a solution. And then you've got pool water, another example of solutions. Different types of solutions. All three, lakes, ocean water, and pool water, all contain water in them, but they have different types of particles floating around in them. Okay? So, in a solution is made up of two components, at least two. There's something called the solute. Okay? You're going to have to know these definitions and know how to identify them. Okay? This is basically sub-objective 1, be able to define the components of a solution. There is a solute. The solute is the substance that dissolves in the solvent. Okay? Typically, the solute is the one that is the minor component, meaning there's not as much of it as the solvent. Okay? So the solute is the minor component. Then the second thing you have is the solvent. The solvent is the thing that does the dissolving. Okay? So an example of a solute is something like sugar. Okay? So I have a glass up here, and I throw some sugar inside of it. This glass has some water in it. I throw the sugar inside of the water. The sugar is going to dissolve in the water. We would call the sugar the solute. The thing that does the dissolving, everything around the sugar, which would be the water, is the one that is the thing dissolving. That's the solvent. So that would be something like water. So again, a solution can exist as gas, liquid, or solid. Just depends on the state of the solvent. Okay? So the major component is the solvent. If it's in a solid and something else is dissolved in it, I mean, it can still be in a solid. That can still be a solution. Same thing with gases. Okay, so like right now in our atmosphere, it's made up of mostly nitrogen. Then there's also oxygen, there's some argon, there's some CO2, there's a bunch of other components. So air around us is a solution, and the solvent vent, the thing that is doing the dissolving really would be like the nitrogen gas, because it's the major component of that. Okay, so solution contains solute and solvent. Solute is the thing that gets dissolved, excuse me. Solvent is the thing that does the dissolving. It's the major component. Now, there can be these things that we're getting ready to discuss are how solutions can interact with one another, how liquids, solids can interact with one another. So, we're going to talk about solubility and something called miscibility. So, there are two types of, whenever you mix a solid with a liquid, one of two things can happen. We can either say that it's soluble. A substance that is soluble is a substance that dissolves in a solution, and we say that that substance is soluble in that solvent. So for instance, something that I would say would be soluble in water would be sugar or salt, NaCl. So if I take sodium chloride, I put it in water, and I stir it, you're not going to see the NaCl anymore. We would say that they are soluble. Okay, so we'd say sodium chloride is soluble in water. Then the other thing that could happen is a substance that does not dissolve in a solvent is said to be insoluble in that solvent. So if I take sand, okay, you might be like, sand doesn't dissolve in water. You're right, that's because it's insoluble. So you take the sand, you throw it in water, you stir it around, nothing happens, right? You still see the sand hanging out there in the bottom of the container. Even if you let it sit there for days, years, it would not dissolve because it is insoluble. Okay, so soluble and insoluble are words that we use to describe interactions between a solid and a liquid. Okay, so the next two type we would talk about is miscibility. This is when we're talking about two liquids. So two liquids that don't mix with each other are said to be immiscible. Okay, so that would be something like oil and water. Okay, I've got an example of that for you. Here is an oil and water mixture. It forms two layers. I'm sure you guys have seen something like this before, but the oil layer is on top, the water layer is on the bottom. Okay, if I shake this up, you might say, oh wow, look, they're mixing. Well, they're actually separating right now before your eyes. That's because they are immiscible. Oil and water do not mix because they have different types of bonding, and we'll talk about that in our next lesson. So by now, there are two layers again. There's that clear layer on top and the green layer on bottom. Two liquids that mix with one another are said to be miscible with one another. So if I take two liquids and I mix them together, we say that they are miscible. So something like that would be something like water and rubbing alcohol. Okay, so if you took rubbing alcohol, water, mix them together, let them sit there, you would not see that two layers. You wouldn't see two different substances. They mix together, and you now wouldn't be able to tell that there are two substances in there. Okay, so that is, there's soluble and insoluble describe solids with liquids. Miscible and immiscible describe two liquids going together. So the next thing we're going to talk about is something called solvation. Okay, solvation is the process of something dissolving. Okay, so in substances we have attractive forces that exist between particles. Okay, so remember when we talked about bonding? Remember when we draw those Lewis structures that we put like carbon in the middle and we draw lines off of it, connect other atoms, and we'd answer the question, is this a polar or non-polar substance? Okay, hopefully you guys remember that. Those forces exist between solute and solvent particles. Okay, when a solid solute, so something like NaCl, is placed in a solvent, the solvent particles, so the water particles, that's the solvent, would completely surround the surface of the solute. If the attractive forces between the solute and the solvent particles are greater than between those of the solute particles, the solvent pulls the solute particles apart and surrounds them. So, I take salt, NaCl, I put it in water. If the salt, okay, if those Na plus ions and those Cl minus ions are more attracted to the water, then the NaCl will break off, the Na will break off of that crystal and get surrounded by water. And then that is the process of it being dissolved. That is the process of solvation. If you put something in water and the particles would rather stick together, in other words, they're not more attracted to the water, then that means it will not dissolve. Okay? It's kind of like, let's say that you're hanging out at a party and you've got a group of friends that you're hanging around and you're chatting it up, and then all of a sudden a group of people walks in that really you're better friends with. Well, what do? Well, if you like the group of friends, if you're hanging out with this group of friends, but you like that other group of friends better, you're more attracted to them, then you're going to leave that group of friends. And we would say that you're kind of like that crystal. You're that substance popping off, being more attracted to the solvent, and you would be getting dissolved. But let's say that you're hanging out, you're talking with a group of friends, and some people walk in that you're like, I don't really care about hanging out or talking with them. Well, then that would be the example of being insoluble. You would not get dissolved because you'd rather hang out with the group of friends you have and the ones you're currently talking to than the ones that just walked in. Okay? Here's the thing that you need to remember about solvation is this phrase, like dissolves like. So what that means is that like charged and like polarity particles will dissolve in particles that are like them. So back to the friend group idea. If you see someone that you more identify with, you have more fun with, you're more the same, you're probably going to leave and go talk to them. Okay? So like particles are going to dissolve like particles. So what that means is, if you have, remember the terms that we use to talk about substances typically is, we have polar substances, we have nonpolar substances. I know I'm going way back into first semester chemistry here. We have polar substances, we have nonpolar substances. Polar substances will dissolve in other polar substances because like charged particles will dissolve in other of particles of the same charge or the same type of particles. In other words, polar particles will dissolve in polar particles. Nonpolar particles will dissolve in nonpolar substances because they are similar substances. But a polar substance will not dissolve in a nonpolar substance because they are not like each other. A nonpolar substance will not dissolve in a polar substance because they are not like each other. All right? So what we have to do is we have to consider the type of bonding. We have to consider what the polarity is. We have to talk about something called intermolecular forces. We're not going to get into that kind of detail in here. Really, all that I want you guys to be able to say is, if I said something like, why doesn't this substance dissolve in this substance? Why doesn't oil dissolve in water? Why aren't these things miscible? Well, it's because water, which is the thing on the bottom, is a polar substance. Oil is a nonpolar substance. So water and oil are not like each other, which is why they do not dissolve. Okay? That's really the type of explanation that I would be expecting from you guys. So here's what happens with water and sodium chloride. And again, on your notes page, what I want you to do is I want you to describe solvation. I want you to take a minute, stop, and I want you to describe solvation in your own words. So write it out however you remember it. Okay, now that you're done with that, what we're going to do next is I want you to draw a sketch of the solvation of water and sodium chloride. Now, here is what water looks like. Here is what sodium chloride looks like. All right? Water is a polar molecule. It has two hydrogens, those are the white spheres, and it has one oxygen, that's the red sphere. Oxygen has a partial negative charge because it's very electronegative. Hydrogen has a partial positive charge because oxygen is stealing electrons from it. So that's why we have these positive and negative ends. Then you've got sodium chloride. Sodium chloride is a crystal that's made up of sodium ions, which are positively charged, and chloride ions, which are negatively charged. So here's what happens. Salt, NaCl, and water, salt is soluble in water, right? We've seen it. We throw salt in water, and it dissolves. Here's why, okay? Here's what happens. As these water molecules start to surround this crystal, Na plus ions, sodium ions, are more attracted to the water than it is to the chloride ions. So the Na plus will leave. Same thing happens with chloride. Cl minus is more attracted to water than it is to the sodium ions. So it will leave. That's why sodium chloride will dissolve. Now here's what's really cool and what happens. I want you to look over here on the right side. Notice the orientation of these water molecules, okay, around the chloride compared to these water molecules around the sodium. So sodium is a positive charge. Notice how the red part, and this is what I want you to sketch. I want you to sketch something that looks like this. This is the sodium ion, and these are the waters around it. Here's the chloride ion, and these are the waters around it. Notice how the negative side of the waters, the oxygen, is facing towards the positive ion. Well, why is that? That's because opposite charges attract to each other. Since the red side, the oxygen on water, is negatively charged, it is attracted to the positively charged sodium. Notice how on the chloride, though, they are opposite of that. Notice how the partially positive charged hydrogens are facing the negatively charged chloride. That's because opposite charges attract to each other. So I want you to draw those two sketches for me up in the solvation sketch of NaCl and water. All right. So now here's the explanation of why NaCl does dissolve in water. So the attractive forces between H2O molecules are stronger than those between the NaCl crystal or those NaCl ions. The H2O molecules are polar, as are the NaCl molecules. Now you might say, well, they're technically ionic, but ionic is like an extreme type of polarity of polar molecule. So they have ionic bonding, and that's why they have this Na plus and Cl minus ions. So hence, NaCl dissolves pretty readily and completely in water because of these things. Because they are, again, remember the phrase I said is like dissolves like. Because NaCl has similar types of bonding and polarity as water does, it will dissolve in water because of that fact. All right? So here are some factors that affect the rate of solvation. What I mean by rate is how fast. So we've been saying like this thing will dissolve or it won't dissolve. But there are some factors really that you guys already know that affect how fast something dissolves. So I want you to imagine, first of all, there are 3 factors you guys are going to fill in, okay? I want you to try and predict some of these. So I want you to imagine you're making lemonade. Do you want your lemonade now or do you want it a day from now? Well, of course, you want it now. So what could you do to make it dissolve faster so that you can drink it as quickly as possible? Think about that right now. All right. So hopefully here are some things that you thought of. You probably didn't say these exact words, but you thought of them. One factor that affects the rate of solvation is something called agitation. Well, what does agitation mean? All that agitation means is stirring. Okay, so if I was making my lemonade, hopefully you said, well, I'm going to stir it, right? I'd put together I'd have my water, I'd have my packet of lemonade, I'd throw it in there, and then I add a bunch of sugar, right? And I just stir. That's agitation. So if I stir something, it makes it dissolve faster. Okay? The next thing that you probably didn't quite think of, maybe you did, is something called increasing the surface area of the solute. In other words, I don't know if you guys have seen or you have sugar cubes. Would you add sugar cubes into your container, or would you add sugar that's all smashed up into small pieces? Well, you're going to throw stuff in that is in small pieces. Because when it says increase the surface area, increasing the surface area means if I take something and I chop it up into little tiny pieces, I am actually increasing the surface area. I know that might seem kind of backwards. We feel like big particles have big surface area, but actually when particles are chopped up, there's more surface area. So you're probably going to use granulated sugar, not sugar cubes, because sugar cubes don't have as much surface area. They don't dissolve as quickly. Okay? This is probably the third one, maybe the one you didn't think of, and that is increase the temperature of the solvent. If I actually make my water hot, stir in my lemonade and my sugar and all that stuff, it will actually dissolve faster. Now, I don't know of anyone who drinks warm lemonade, so that wouldn't really work in our lemonade example, but it does speed up the rate of solvation. Okay, so that finishes up our lesson today over solutions. So go ahead and answer these questions at the end of your video. Thank you for watching.